We're going to do a maximization problem involving folding a piece of paper into a box. And we're going to figure out the volume of the box. And this is problem number 98 on page 148. So let's follow along. It's asking to make an open box with locking tabs is to be made from a square piece of material 24 inches on a side. This is to be done by cutting equal squares from the corners and folding along the dashed lines shown in the figure. So basically what you're going to do is you're going to do a double fold on the sides and a single fold on the edge. So we're going to pretend that you are now the person to figure out how to make the best box. Because what's going to happen here is we're going to have to buy cardboard. And the cardboard's coming in at 24 inches on a side. It's a flat piece. And we got a machine that's going to fold these double edges. I don't know why they want the double edges. It's just one of these typical math problems, to make it a little difficult because it's no longer just a simple one. We've got to figure out what's going on. So let's just draw a quick rough sketch of what's going on here. So I have this square thing here, and it's going to fold up. And as you see, I'm going to lose some of my distance here, and I'm going to lose some of my distance here. And so we have to ask ourselves, well, after we make these folds like this, what is this distance, okay? That we're going to really free the true base of the box being. And then what is this base going to be? This length this way. Well, if we look at this thing from the drawing, we see that the edges are turned up. And so if we've got ourselves a nice little box drawing, okay, let's draw ourselves a nice little box drawing. And this is what the little box drawing is going to look like. It's going to look something like that. And let's see if we can make the little box. And this is what the little box is going to look like. Okay, got it. So that's our little box. And oh, we got a little edge here. We could see this edge if we look inside the box. And it's going here. We can see this, but we cannot see that edge. We can see this edge. And okay, that's the box. And this is the inside of the box. Okay, so that's what we're looking at. Now, this height of this box is x. And the question is, so x is going to equal to h. And I'm going to label this one here on the front. I'm just going to call this length here, for lack of the width. Okay? And remember, it's base times width times height is your formula. So over here, I'm going to go here to here, and this dimension here, we're going to call B for base times height times height. Base times width times height. Okay, I think that's how it works out. Base times width times height. So we're going to come over here, and we're going to write the formula. So the volume of a box is base times width times height. Now, if we could put all these equations in terms of x, well, wait a second. We have one already. We have this one. We have h. Really, h here is a function of x. So h as a function of x is just x. Okay, that's an easy function. It's an identity function. Whenever we put x in, if x is 2, h is 2. X is 1, h is 1. X is 5, h is 5. So whatever h is, or whatever x is, h is. Okay, so, well, the question then is, well, this thing here is 24, right? It's 24 inches by 24 inches. But that's the flat piece. But the question is, what's W? Well, let's just say this is W, up here. That's W. What did we do to get W? Well, we started with 24 inches of material. We took away this side, this side, this side, this side. That's that double fold area. So I think W now that's as a function of x. And I think that's the whole width, 24. And we took away 4 x's from it. And that works out that. That's all x's on the right side. So now let's try b as a function of x. And if we go back to our drawing, we see that we took away an x here. Okay, we took away an x here, and boom. Hey, here we got 24 minus 2x. Okay, that's not too bad. So now we can come back here and really make our volume equation all as functions of x's. So let's go, let's zoop in b. What is b? b is 24 minus 2x. Okay, what is w? W. Oh, let's zoop that one in. 24 minus 4x. And finally h. Let's zoop that in. That's x. Well, I don't think I'm going to do much more with that. I'm just going to go ahead and put that in my calculator. And let's come back to talk about that in a second. Okay? Okay, we're back here live now, and we've put this in a calculator. So here's the equation, and I hit zoom standard, and presto, wonderful. This is what we see, a line, and I have no idea what that is for. Either way, well, what we should see is some equation that tells us where we want to go ahead and cut this, or fold this box at. So what are we going to do? Well, let's talk about domain. So right now, let's look at this problem and see, is there any insight we have with domain? What's the size that x might be? Well, if we start out with a very little box, we could take a box and almost literally not even fold anything up. And if we did that, we would have a lot of width, okay? But we wouldn't have much of a box. You could see that this box would hardly hold anything, okay? So it would like be a nothing box. Okay, well, I don't have enough room on the paper here to finish it. I don't want to draw on the desk. But this would have no volume. No volume. Let's go down here. Volume. No volume. So that means that x has to be something. So our domain, we want to say, first of all, our domain has to be something. So it has to be greater than 0. Well, then how big could this thing be with x? The question is x. Well, if we took all our material and folded x this way, we could say, okay, 24 divided by x here and here. We could take 12 and 12 here. Well, but that'd be fine, but can we do 12 and 12 here? No, because I need 12 here, 12 here, 12 here, 12 here. That would be 48. I don't have enough material. So wait a second. If I do 6 here, 6 here, 6 here, 6 here, that would make a nothing box vertically, like so tall. Here's what my nothing box would go, way up. And it would be a nothing box going way up. Okay? It's a nothing box. Because why? Because it doesn't have any width, doesn't have any base. It would just be a tall box. And we literally, what would that look like? That would just be a line. That's all that would be, is a line. Because all the material would just go up in a line. That wouldn't work either. So what we realize is that our domain goes from 0 to 6. Now, we've got to use that because we've got to figure out what our calculator is going to look like. Because here's what happened. This is a nothing print, okay, on our calculator. So let's go back. What's our range going to be? What's our output? What is volume going to be? Volume. We got to find volume. Well, we got to do what? We got to just guess. Let's put 3 in here. Let's just guess. So volume, when we just pick 3, is going to be 24. Let's see, 24 minus 6. What's 24 minus 6? It's 18. I hope that's right. Okay. And what's 24 minus 12? Well, that's, see, 24 minus 3 times 4 is 12. 12. And what is 3 for x? 3. Okay. Well, what's this equal to? Well, do I really need to know what? I'm guessing 3. So why don't I just guess what that is? Well, what is that? I don't know what it is. Let's see. 12 times 3 is 36. Okay. That's 36. And 18, oh, that's 18. So what's 18 times 36? Do I really know what 18 36 is? What do I know? I want to find a volume. How about if I just estimate? Go a little bit bigger. Pick an easy number bigger than 18. I think the easiest number bigger than 18 is 20. I like 20. Okay? And what's the next easiest number bigger than 36? Well, I like 40. I could do 40 by 20 in my head. So I could estimate 800. I could estimate 800. Let's see what happens. Let's do that. Let's go to our window now. And let's put in our window, okay, in our window, let's put 0. I like to go a little bit less just to see the vertical axis, which is called the ordinate. Okay, I like to see the ordinate and the horizontal axis, which is called the abscissa. I don't know, I've just got this thing. My teachers in high school told me that's what we should call them. And so I'm going to go -1 to 7. I'm going to leave it at 1. And then for the y-axis, I'm going to go from nothing, which maybe nothing would be, if I'm going to 800, maybe I'll go negative 50, and then I'll go to, let's try 800. Let's see if that'll work. And I'm going to go by 100s here. I don't know why. I just decided, and let's graph it. Let's see if we could see something max. Well, how about that? There it is. Well, this is 1, 2, 3, 4, 5. So let's do it. Second, calc, max, 4. And the left bound, I just want the left bound to be 1. That's all, 1. And the right bound, if I remember, the right bound could be like, what this thing went up to 6, right? So I'm going to put 5.5. That's 15.5. How about 5.5? Hit delete, delete. Okay. Oh, wait, that says left bound. No, I want to do 1 for left bound. Hold on, let's clear that. Let's put 1 for left bound, enter. The right bound, we're going to put 5.5, enter. And guessing, I'm just going to go 1 click to the left and see if it likes it. It's a curve, it's fine. Oh, there it is. So we find that the volume is maximized when x is 2.53, x is equal to 2. Well, let's round it to 54 inches, and the volume we get, the maximum volume we get, the most volume at 2.54 inches for this thing. So if we're working at that factory of making those, we can tell our customers, you come with us, we'll sell you the maximum volume box for the price, and we'll fold it up just the way you want it, and you'll get a volume of 665. Oh, that's cubic inches. Cubic inches. We always seem to find something there. Okay, that's it. Hope this helped.